Continuing the chemistry of phosphorus as a member of nitrogen family, group 15 on the periodic table, phosphorus has 5 valence shell electrons available for bonding. Its valence shell configuration is 3s2 3p3. Phosphorus forms mostly covalent bonds. Any phosphorus rock can be used for the production of elemental phosphorus. Crushed phosphate rocks and sand silicon dioxide react at 1700 Kelvin to give phosphorus oxide P4O10. Here we see this reaction. P4O10 phosphorus oxide can be reduced by carbon. In this reaction below we see it gives P4 and 10 molecules of carbon monoxide. Waxy solids of white phosphorus are molecular crystals consisting of P4 molecules. They have an interesting property in that they undergo spontaneous combustion in air. Phosphorus reacts with oxygen. Here again we see the reaction to give phosphorus oxide. The structure of P4 can be understood from the electronic configuration, that is S2 and P3 of phosphorus in bond formation. Sharing 3 outermost electrons with other phosphorus atoms give rise to 6 phosphorus-phosphorus bonds, leaving a lone pair occupying the 4th position in a distorted tetrahedron. When burned with insufficient oxygen, P4O6 is formed. To each of the P phosphorus-phosphorus bonds, an oxygen atom is inserted. Burning phosphorus with excess oxygen results in the formation of phosphorus oxide again, that is P4O10. Then here we see that oxides P4O6 and P4O10 share interesting features. Oxides of phosphorus. They dissolve in water to give phosphoric acid, that is also an important compound of phosphorus. Phosphoric acid is a polyprotic acid and it ionizes at 3 stages. These stages are shown below. Then phosphoric acid is a polyprotic acid which makes it an ideal buffer. It gets harder and harder to separate the hydrogen from the phosphate, making pKa values increase, and the conjugate bases can be mixed to form buffer solution. Here the various dissociation constants are shown in this tabular form, and the ionization constant for the successive deprotonation of phosphoric acid states. First, dissociation constant, second Ka1, Ka2 and Ka3, and the overall ionization constants are given. Now presently the phosphorus is used commercially as phosphorus compounds. They are used in the manufacture of phosphoric acid, used in soft drinks and fertilizer compounding. Other compounds find applications in fireworks and of course phosphorescent compounds with glow in dark. Phosphorus compounds are currently used in foods, toothpaste, baking soda, matches, pesticides, nerve gases and fertilizers. Phosphoric acid is not only used in buffer solution, it is also a key ingredient of Coca-Cola and other sodas. Phosphorus compounds were once used in detergents as a water softener until they raised concerns about pollution and eutrophication. Pure phosphorus was once prescribed as a medicine and an aphrodisiac until doctors realized it was poisonous. Now we come to the chemistry of antimony. Antimony and its compounds have been known for centuries. Scientific study of the element began during early 17th century, and much of the important work was done. The name of the element comes from the Greek anti plus monos, that is not alone. Then antimony is a hard, brittle metalloid alloyed with other metals to increase the hardness. It is also used as some semiconductor devices. That is important use. The recovery of elemental antimony parallels the arsenic. The sulfidose stibnite is roasted in air and then heated with carbon. Antimony trisulfide. Compound of antimony is a sulfide mineral commonly called stibnite or antimonite. Antimony's trisulfide exists as a gray-black crystalline solid, that is orthorhombic crystal, and an amorphous red-orange powder. It turns black due to oxidation by air. Antimony trisulfide is the most important source for antimony. It is insoluble in water and melts at 550 degrees centigrade. This symbol SB is derived from stibnite. Amorphous red to yellow-orange antimony trisulfide is prepared by treating antimony trichloride solution with hydrogen sulfide. Here the following reaction is given. When melting antimony trisulfide with iron at approximately 600 degrees centigrade, the following reaction yields elementary antimony. So the elemental form of antimony can be obtained from this antimony trisulfide only. It is used as a pigment in pyrotechnics, glitter and fountain mixtures, and as safety matches. In combination with antimony oxides, it is also used as a yellow pigment in glass and porcelain. Antimony trisulfide photoconductors are used in Vidicons for CCTV. Now, the chemistry of bismuth, the heaviest non-radioactive naturally occurring element. It is hard, brittle metal with an unusually low melting point. Alloys of bismuth with other low melting metals such as tin and lead have even lower melting points and are used in electrical solders, fuse elements, and automatic fire sprinkler heads. The metal can be found in nature, often combined with copper or lead ores, but can also be extracted from bismuth oxide by roasting with carbon. Compounds of bismuth are used in pigments for oil painting, and one is in popular paint preparation for the treatment of common stomach upset. Now the last element discovered so late, that is moscovium, with the atomic number 115 in studies announced jointly by the Joint Institute for Nuclear Research in Jubna, Russia, and the Lawrence Livermore National Laboratory in US. 4 atoms of elements 113 were produced in 2004 via decay of element 115 after the fusion of calcium and americium. Now, summary of this group 15. Nitrogen and phosphorus behave chemically like nonmetals. Arsenic and antimony behave like semimetals, and bismuth behaves like a metal. Nitrogen forms compounds in 9 different oxidation states, of which +5 oxidation is stable and it decreases further because of the inert pair effect up to the bismuth. Due to their high electronegativity, the lighter pnicogens form compounds in -3 oxidation state also. Because of the presence of a lone pair of electrons on the pnicogen, neutral covalent compounds of trivalent pnicogens are Lewis bases. Nitrogen does not form stable catenated compounds because of the repulsions between lone pair of electrons on adjacent atoms, but it does form multiple bonds with other second period atoms. Nitrogen reacts with electropositive elements to produce solids that range from covalent to ionic character. Reaction with electropositive metals produce ionic nitrides. Reaction with less electropositive metals produce interstitial nitrides, and reaction with semimetals produce covalent nitrides. The reactivity of the pnicogens decreases with increasing atomic number. Compounds of the heavier pnicogens often have coordination number of 5 or higher and use dsp3 or d2sp3 hybrid orbitals for bonding. Because phosphorus and arsenic have energetically accessible d orbitals, these elements form pi bonds with second period atoms such as oxygen and nitrogen. Phosphorus reacts with metals to produce phosphides. Metal-rich phosphides are hard, high-melting, electrically conductive solids with metallic luster, whereas phosphorus-rich phosphides, which contain catenated phosphorus units, are lower melting and less thermally stable. The most important highlight of the summary is the reactivity of the heavier group 15 elements, which is also group 5A, decreases down the group, as does the stability of their catenated compounds. Some of the problems and their solutions are given in the following sheets. The problem related to the nitrogen. Here we have the balancing of completing the reaction, and the further completed reactions are given in the next sheet. What are the different isotopes of nitrogen? Then their various oxides are given, and their questions related to the uses of nitrogen. Here are given the completed reaction, balanced reaction of the previous questions, problems. Now different isotopes of nitrogen and larger type of questions are given. Then some of the problems related to nitrogen, phosphorus are given in this sheet, and again the completing chemical equations and their balanced chemical equations are given in the last. Their solutions are given. Then structure and reactivity problems. These problems are larger questions related to the structure of the various elements of nitrogen, phosphorus, arsenic, antimony, and all other metals. Next, the last is completed reaction, balanced reactions of these nitrogen group elements.